Now, this word collaboration, I'm going to stretch it a bit. You all heard Sloan's talk the other day where she was talking about, yeah, right. Who are you talking? My brain. About Veblen, right. And you saw she had a list of all his papers that were co-authored with other people. And then she talked about all these groups that are doing research on various aspects of Veblen's life and how they're collaborating. Well, I mean, collaboration today or even 100 years ago was by people getting together and talking, or if not getting together physically, then then talking on the telephone, or maybe sending letters back and forth until they worked out something. Now, obviously, people didn't do that 1,000 years ago, or 2,000 years ago, or 3,000 years ago. There wasn't. Mathematicians were scattered both geographically and temporally. So one person learned of another's work only by reading somehow or finding out somehow what that other person had done and then reacting to it. Now, they couldn't go back and forth because if you were reacting to somebody who lived 300 years earlier, it was difficult. So we're just going to look at four problems that people looked at over a long period of time in different cultures and different languages, and where it seems that they knew what the previous person did somehow, and we don't always know how. In fact, we generally don't know how. But we'll see what we can find out. We want to begin with a problem that any of you who have studied history of mathematics probably oops. Okay, what did I do? Probably have seen. The Moscow Mathematical Papyrus has this problem about calculating the volume of the frustum of a square pyramid. It was surprising to those who studied Egyptian mathematics that such a problem was there. Nevertheless, there it was. The problem says if someone says to you a truncated pyramid of 6 for the height by 4 on the base by 2 on the top, you are to square the 4, the result is 16, double 4, the result is 8, square the 2, the result is 4, add those numbers together, the result is 28. You take 1/3 of the height 6 and you get 2, multiply 28 by 2, and you get 56, and that's the answer. Okay, now, we could write down a formula. It's down at the bottom there, the volume being 1/3 h times a squared plus b squared plus ab, where there's the pyramid, or the frustum of the pyramid. A lot of ink has been spilled in trying to figure out how the scribe, how they found out this formula. I mean, it's correct. People have tried to see, did he divide it up into other pieces or what? Nobody's gotten a good answer, and we really don't know. Okay. But we do know that over the years from this is maybe 1700 BCE, we don't know exactly. Over the next 1,000 years, 1,500 years, people did learn, certainly knew how to calculate the volume of a completed pyramid. And if we were asked today, how would you calculate the volume of the frustum of a square pyramid, we would probably use similar triangles to figure out the total height. Find the height, then find the volume of the top piece, and find the volume of the whole piece, and then subtract. But clearly that was not done then. Okay. Where does this problem appear again? The next time we see it is in a papyrus. It's called the Papyrus Reineer, after the person who dug these out of the ground. This is part of a collection of Greek manuscripts held in Vienna. It was originally excavated in the late 19th century. About 100 kilometers south of Cairo. And there's what the scribe writes. Given a square truncated pyramid whose lower base is side 10, upper base is 2, and whose slant height is 6, find the volume. Okay, now it's the slant height. Instead of the height, we're looking at the slant height, which obviously is actually easier probably to measure in the field than the actual height. But then he goes through the thing. He gives you a procedure for finding the actual height, and then he goes the same procedure as before. excuse me. He has a different procedure. He said, now add the 2 to the 10, making 12, of which half is 6, multiply it by itself, giving 36, then subtract the 2 from the 10, those were the upper base and the lower base, giving remainder 8, of which half is 4, multiply that by itself, giving 16, of which 1/3 is 5 1/3. Add this to 36, giving 41 1/3, multiply by the height 2, and you get 82 2/3. Well, that looks like a little more complicated procedure, but let's look at the formula just so you can see it. I mean, he first calculates the height from the slant height by using the Pythagorean theorem twice. And that's basically, he does it by s squared, the slant height squared, minus the difference between the top and the bottom squared over 2, and taking the square root. That's the Pythagorean theorem. And then he uses the formula of the volume is the height times this a plus b over 2 squared plus 1/3 a minus b over 2 squared. Now, a little bit of algebra, you can reduce that, the volume formula, to the same volume formula we had before. Well, did the original Scribe back 1700 BCE do it that way? We don't know. Did somehow this get transmitted? Well, certainly people would have been interested in this problem. I mean, this is in Egypt. They were building pyramids. It would be very useful to know how to calculate the volume of a partially built pyramid. Okay. But there's no proof here. It's just directions for doing it. Like on a lot of documents from ancient times, it's just directions. Okay. Well, we find a proof, more or less, in the Metrica of Heron. Now, Heron, a lot of you are familiar with. We don't really know his dates. Mostly he's thought to be in the 1st century CE, but he could have been later, probably not any earlier. Anyway, in his Metrica, he shows how to calculate a truncated pyramid with a triangular base. Okay. Let's just look at the, what do I do here? There we go. This is basically his argument for how to calculate the volume of a pyramid with a truncated pyramid with a triangular base. It looks a little more complicated because you have this square root of 3 over 4 business, but that's basically how you need that to calculate the area of a triangle, of an equilateral triangle of given side. Now, he doesn't use square root of 3 over 4. He uses a very good approximation to it. Okay. And there's the diagram in what we're using today, but it basically means, Heron basically shows how to divide up this pyramid into pieces that enable you to make that formula work. Okay. Does this problem appear in Europe? Well, it does. We can see it in Europe in the Leonardo of Pisa, Fibonacci, his De Practica Geometria of 1223. Now, he states it differently. He says for a truncated pyramid with a triangular base, he proves that its volume is 1/3 the product of the height by the sum of the areas of the upper triangle, the lower triangle, and the area that is the mean proportional between the two triangles. And he does that with a fairly good geometrical argument. You know, he then claims that a similar demonstration shows that if the base of a truncated solid is any other shape at all, everything is valid, which is pretty clear. Okay, and that's basically the same formula we had way back, because the square root of the mean proportional between a squared and b squared is obviously ab. All right, now can we call this a collaboration? These are 4 different people from 4 different areas and locations looking at the same problem. Did the later ones learn from the earlier ones, making the solution easier to understand and generalize? 2 of them gave some sort of proof, Heron and Leonardo. But in some sense, this is how collaboration ought to work, right? People look at each other's work, try to improve it. Can I prove what the other guy did? Can I prove it a different way? Can I generalize it? Whatever. This is what happened. How did the knowledge get transmitted from one place to another? That's a little trickier. We have no good way of knowing. Documentation is very scarce. I would guess that most likely the way these things were transmitted was orally. And of course, we don't have any record of that. But it was an interesting problem that people kept looking at. Now let's look at another problem. Starting back maybe 300, it just keeps going off. There we go. Starting back at about 300 BCE. Now, everyone is probably familiar with the fact that the ancient Babylonians knew how to solve quadratic equations. And that was back 1800 BCE or thereabouts. But there's a group of Babylonian tablets that date from the Seleucid period, say around 300 BCE, when the Eastern Mediterranean was under Greek influence, for sure. And in those tablets, the Babylonians did it differently. Here we're going to look at how you deal with finding the length and width of a rectangle if you know certain pieces of information, like the sum, in this case, the sum of the length and the width and the length of the diagonal. I mean, it's a quadratic problem, but basically what the scribe in this tablet does, and I don't need to read it to you because it's basically looking at this diagram. I mean, the diagram isn't there on the tablet, but this is clearly what the scribe is thinking about. It's saying, you know, if you look at this picture, you can see that the square on the sum of the length and the width less square on the diagonal is twice the area of the rectangle. Well, it's really the four triangles which make up twice the rectangle. And secondly, when you subtract 4 times the rectangle from the square on the sum of the length and the width, you're left with the little square in the middle, which is the square on the difference of the length and the width. And if you know the sum of the length and the width and the difference of the length and the width, it's obviously easy to find both the length and the width, which is what the scribe did. Okay, so that was 300 BCE, maybe. If we look at, let's see, there's been a papyrus dug up in Egypt that has been dated to around the same time period. 250 is a very rough estimate. This is in Demotic, which was an Egyptian script, okay? And it's basically the same thing. A plot of land that amounts to 60 square cubits, that's the area that is rectangular, the diagonal is 13 cubits. How many cubits does it make to a side? And again, the scribe, what he does is, you know, he squares the diagonal, he doubles the area, he adds those two together, it takes the square root, and so forth. It's the same argument, it's slightly different conditions. Here you're given the area and the diagonal instead of the sum of the length and the width and diagonal. But basically, you're using the fact that the square on the diagonal added to twice the rectangle is the square on the sum of the height and the width, and the square on the diagonal less twice the rectangle is the square on the difference of the height and the width. And of course, again, once you get both the sum and the difference, you have each of them. Now, a little bit later, we have a Latin manuscript by a Roman surveyor by the name of Marcus Junius Nipsus. He wrote this work. It's called Podismus. Now, he was dealing with triangles, right triangles rather than rectangles, but it's the same problem. Given a right-angled triangle with hypotenuse 25 and area 150 to find the two sides separately. So it's the same as the rectangle problem. And again, he does the same kind of thing. You square the hypotenuse, you add 4 times the area, you take the square root, and you go on from there. The square on the hypotenuse added to 4 times the area is the square of the length plus the width, and so forth. And he does it the same way. Okay, so again, there's 3 people. Let me go back a second. There's people from over a period of several hundred years, one on a Babylonian tablet, one in an Egyptian manuscript, and one in a Latin document over a period of, say, 300-400 years, doing the same problem. Did they learn from each other? That's an interesting question. Did they collaborate? Well, we can talk about that. All right, let's look at a third problem that also goes back a long way. How do you find the area of the segment of a circle? Okay, there's a circle, the radius r. The segment is the little piece at the top. Base I've labeled c, and the height is h. For later reference, beta is the arc length, but we don't have to deal with that right now. Heron mentions that there are two ways to do it. He says there's an ancient method where you take the area is simply 1/2 c plus h times h. And he shows that if you take the ratio of the circumference of a circle to the diameter as 3, then this gives you the right answer for a semicircle. You can check that out easily enough. But he says there's a better method, a newer method. We add to the first expression 1/14 c over 2 squared. And he says that way, if you take the ratio of circumference to diameter to be 3 1/7, which he was certainly familiar with, that was basically the Archimedean value for pi, then, again, this formula is accurate for a semicircle, which, again, you can check easily. Curiously, in the Metrica itself, which is a pretty detailed textbook, he doesn't actually do any examples of this except for the semicircles themselves. But in another work called the Geometrica, which is attributed to Heron, but probably was written by students of his, probably somewhat later, and it has no proofs at all, although, I mean, Heron's metric has some proofs, but the Geometrica doesn't. There, the author, whoever it is, whether it's Heron or not, goes through a problem, an actual numerical problem. The base is 16, the height is 6, find the area. And he says, add the height and the base, half of, you get 22, half of 22 is 11, multiply by the height to get 66, half the base is 8, square it, 64, take the 14th part, 4 1/2 on a 14th, add it to 66, and there you go, 70 and 1/2 and 1/14. Just for your information, if you want to know how good this approximation is, the correct value is 70.708. Heron's value is 70.5714. That's not bad. Now, this same problem shows up again in Latin documents. Okay, here is Columella, who is a Roman farmer who wrote this massive text on Roman agriculture. But one of the chapters of that was about measuring fields. And so he measured a field that was in the shape of a circular segment. And he doesn't say, he uses exactly what Heron's rule, his second rule, about taking c plus h times h, and then you take c over 2 squared and take 1/14 of that. And he gets the answer. He just leaves it as approximation. He says it's about 44, even though he says he takes a 14th part of 64, which makes 4 feet and a little more. Well, actually, the 14th part of 64 is more than a little more than 4. It's 4.57. But anyway, his answer is 44.57. The actual value, if you do it with modern techniques, it's 44.73. And certainly for a field, that's close enough. Okay. A very interesting thing is if you look at another surveyor about a couple hundred years later, he writes the same problem down pretty much. Suppose there's a field in the shape of a segment of a circle, but less than a semicircle, where the base is 20 and the latitude 5 perdici, which is some measure. Now he says we add the latitude to the base, which is 25, and multiply by 4. So wait a second, where's the 4 come from? You're supposed to multiply by 5, by the height. It looks like he was copying from Columella. That's what it looks like to me. He was copying, and Columella multiplied that by 4 because Columella had the height being 4. This guy has the height being 5, but he still multiplies by 4. And so then he goes through the rest of it. So his answer of 57 is way off because he didn't even. So he was reading it, and that's what happens when you read it and you don't understand it. You make bad errors. Okay, well, so maybe that's not a very good collaboration. This problem continues long into the medieval times. Here is by the 10th century, and this is in the Arab world, the Islamic world, people were doing the area of a segment of a circle using the arc length. Now, Ibn Abdun, well, to do the arc, in other words, they were calculating the area of a sector, then they taking the area of the isosceles triangle and subtracted. Okay, the area of a sector is r beta over 2. That's not obviously we know that. Okay, the radius is easily found if you know c and h. You can calculate that yourself. C squared over 8 plus h over 2. Ibn Abdun asserts, I don't know exactly why, that the arc length is given by this formula. Beta is h plus 1/7 h plus 2r minus r minus h. I mean, now I wrote it in modern formulas. I mean, he wrote it, set it out in words, of course. I just want to make that clear. I don't know where that formula came from. It's exact for a semicircle. It's for a quarter of a circle, it's not exact. It gives 1.628 r rather than the exact pi over 2r, which is 1.57 r. But it's interesting. I mean, these people knew some trigonometry, but they didn't use it. But just another 100 years later, Abraham Barria in Spain, he did it by actually calculating the length of the arc. He developed a table to calculate the length of a table relating arcs to chords based on a radius of 14. That was a nice number because that makes the semicircuit's circumference 44. And for each chord length from 1 to 28, he calculated the length of the arc. In any given sector problem, he first calculated the diameter, then multiplied the given chord by 28 over d, so that you convert to a circle of diameter 28, then use the table and then convert it back. So this was the first use of trigonometry, basically. Okay, I had intended to do one more problem, but it looks like I'm out of time, so I will stop with there. But there are lots of problems that one can see that have gone from way back 2,000 years BC up to the Middle Ages, where the same problem appears. People seem to be using more or less the same technique, although sometimes they're improved. And this is the best we can say about collaboration in these times. People clearly have not talked to one another, but they have somehow learned about one another. And this is a question, as I said earlier, that we really don't know exactly how they learned about one another. Most likely, there's an oral tradition. These are problems. People like to solve problems. And we can imagine people traveling between one area and another and saying, I have an interesting problem to solve. You want to see it? And then people learn about these problems. And somebody says, well, I can solve that a different way. And I think that's something we can only speculate about. There's not going to be any documents. We're not going to see any documents tracing these kinds of things. But it's an interesting question about collaboration. So mathematicians do as they've always done. They look at what other people have done. They try to improve it. And so mathematics moves on. Okay, thank you for your attention.
So I do want to thank Sloan for organizing this session and also for her really wonderful talk yesterday morning that I think set the tone of what a collaboration can be in a pretty broad sense, which Victor has just expanded for us. When I got the invitation to speak in this session from Sloan, thinking about editorial collaborations was sort of natural for me. I've been working with Amy Ackerberg-Hastings, who we'll hear from later in the session, editing Convergence for the last 5 years, and then through the Triumphs grants, various editorial collaborations with authors. Those are quite different kinds of collaborations. So that's sort of on my mind. And almost all of those have been done almost entirely through email, which is today's modern epistolary kind of collaboration. Thank you for helping me with that, Sloan. So I picked two examples of these sorts of collaborations, which I'll share with you today. One is a French example, late 19th century, Will and Darboux on the Bulletin, and then a quite different kind of collaboration between Dedic and Vber in the German context on Riemann's collected works. I think it was really super nice of the French and the German to face the opposite direction so they look like they're looking at each other, right? Yeah, that was nice of them. And then my abstract, which hopefully maybe nobody read and I don't have to tell you this, but my abstract promised to come back and do some reflection at the end on what these examples might tell us about successful collaborations writ large. That's way too much to have tried to promise, both for time and for other considerations, but I'm going to try to come back and at least do one sort of closure slide. So I'm going to start with the French example, and I'm going to actually spend most of my time talking about this French example of an editorial collaboration. The Bulletin, you can't hardly see this, but it was really conceived in 1869. You can see up here it was created by l'École pratique des hautes études. It was really sort of the brainchild of the French mathematician Michel Charles in 1869. Its first volume, this is the first issue actually in 1870, began publication in January of 1870 under the direction of Darboux. Okay, we'll change pronunciations as we go along. This is an interesting journal because it was from the very beginning and all along intentionally international, but for very nationalistic reasons. So let me say a word about this. Let me actually let Darboux say a word about this. I have excerpts from these letters between these collaborators that I'll use throughout. Here's Darboux writing to Will early in 1870, or early in the collaboration, 1871, saying he's worried. He's thinking about what's happening in the French mathematical education context. The Germans are already getting the better of us. The Italians are going to do this soon if we're not careful, right? We need to do something about this. And with this bulletin, let's light this holy fire under the French, right? Get the French mathematicians thinking about this, that there are other things in the world to understand besides what's happening in France. So in the sense the French mathematical research community had become very isolated from what's happening in, for example, especially Germany. So this is an 1871 letter. 1871, if you can see here now, I didn't point this out, but now both Darboux and Will are both listed as lead editors here. And the contents of this journal are really carefully thought out in terms of if you want to bring this realization of what's happening elsewhere in the world into the French context, what should be there. So book reviews, article reviews, this mélange section is really key. There's longer articles that feature research either by a particular mathematician or translations of works done elsewhere in the world outside of France. I should say that the reviews and the featured research could be by French mathematicians as well, but so it was international, truly, French and elsewhere. And then when there was space in the journal at the end, they would do this list of recommended books. So it turns out that Julien Will, who you maybe haven't heard of before, was actually super well suited to be this collaborator on this endeavor. So he had this really strong mathematical background. He was a really committed, respected teacher. It turns out that his work at the lycée level, his secondary school teaching experience was not so good. He apparently wasn't that good at that. But having that lycée teaching experience was important to Darboux and his collaborators because he wanted this journal to also be of interest to teachers, not just to researchers, but to actually reach the educational community as well. Will was in Bordeaux, so he's far removed from Paris. But one of the important things that he did there was he was an archivist for the Société des Sciences Physiques et Naturelles. This meant he had access to lots of international journals from around the world, but he also had this really strong network of correspondence from other countries. The other really important talent, I should say, that Will brought to this endeavor is he was a multilingual translator. So even by 1866, he had translated these works in non-Euclidean geometry into French, This is how the French mathematical community learned about the works in non-Euclidean geometry. He translated at least 5 different languages. And one of the other works that we'll hear about again later in the talk that he translated and brought it to the French awareness is Riemann's work. And particularly, this is his habilitation thesis on representation of series by trigonometric functions, where the Riemann integral is first defined. And Will's French translation appears in the Bulletin in 1873. So more about that later, okay? Well, what about Darboux? Well, here's what he brought to this endeavor. He was young, and he was energetic, and he was really super talented. You can see this age difference, right? They're quite different generations. He also has very strong mathematical training. You'll notice he did his doctoral work under Charles, so he was kind of the chosen child when Charles was picking an editor for the Bulletin. Darboux was the first, he was who he wanted. Darboux was actually really well known for excellence in teaching. You'll see he also started at the lycée level. He was apparently more successful than Will, but he gained this reputation early on through his work in the Bulletin and quickly moved to the École Normale Supérieure and the Sorbonne. And then, importantly, he was a highly respected researcher. So first in geometry, which was his doctoral field. But also, he made important contributions in differential equations, ODEs, and analysis. And that work is kind of interesting because he largely became aware of those problems because of translations that Will did for the Bulletin of work that was being done elsewhere, right? So this collaboration, this Bulletin, affected Darboux's work in lots of ways. So I'm going to share some excerpts from letters. Kind of from the beginning, both these individuals were pretty involved in every aspect of this editorial endeavor. So this is Darboux writing about, what do you think? Should we have this list of memoirs like in the Zeitschrift? How should we do it? Should we have, but they end up deciding not to do this by the end, in the end, right? So this is like when they have space available, they list recommended books, but they decide this is not a good idea for the Bulletin. Also, they need access to these papers from elsewhere, right? So there are certain journals that Will has access to in Bordeaux, but they kind of divvy this up. They're like, which ones can you get? And a lot of times they're actually subscribing to them themselves personally, right? So they have access to these other journals. They both work really hard to find other collaborators for this endeavor, right? So this is Darboux writing, saying, oh my gosh, so Simon was horrible. I gave him the works of Lagrange to review. He took the works, he took the subscription to the Bulletin, and then he didn't do anything in exchange, right? So they have trouble finding these other collaborators. And you'll notice actually most of the letters are written from Darboux to Will. That's because the Darboux archives are better preserved, but there are letters from the Will archives as well. Here's Will saying, yep, I can't find anybody to actually, I write letter after letter, I can't get anybody to collaborate with us. So this means that a lot of the work falls on the two of them, right? So if you read the early reviews and you read the mélange, they're written by Darboux, they're written by Will. And that includes translations. I like this particular excerpt because here's Darboux saying, wow, I'm so glad you're making sense of Riemann because I can't, right? His memoirs are very obscure. And it's also interesting because this is also a letter from Darboux to Will about the same Riemann habilitation dissertation, where you could tell from Darboux's response that he's saying Will was apparently not wanting to do translations for the Bulletin. He's complaining about it, maybe because he didn't want to do them, I don't know. But Darboux's saying, yeah, I think it's actually just as good to have these translations as it is to have analysis of research. Well, this issue of translations is a place where Will does eventually change his mind and come to see that translations are a fine thing to have. And this will come at the end of this excerpt, which is actually one of my favorite letters to read, because here's Will complaining to Darboux that Darboux wants to put the Bulletin on a diet for those savages who, when they have nothing else to eat, stuff their bellies with dumplings of dirt, right? So it's like, you just want our readers to have dirt balls, right? That's what you're trying to feed them. So this is an interesting complaint. He's complaining because there's this memoir by Cauchy. So it's this 1825 memoir that was written by Cauchy. It's Cauchy's first paper on integration of complex functions, actually written in 1822, but published in 1825. And if you look at these dates, the letter's being written in January 1875, but already in 1874, Darboux has started to reprint the Cauchy memoir. So obviously he didn't get Will's opinion about whether this was a good thing to do in advance. He just did it anyway. Will says, I know this is a masterpiece, but really we need to put our selves at the service of students, not archaeologists. Like, this is an old thing. Nobody's going to be interested in this. Will's very upset by what this decision Darboux has made. And this is where we can see he's come around to translations are okay. I get this. But, and that's kind of interesting. You hear that international flavor again, because it's not just the French who will benefit from our French translations of Riemann, so will anybody else, like Italians who probably read French better than they read German. This year, 1875, turns out to be sort of a crisis year in this collaboration. You hear this here especially. This is a lot of work, right? And Will is saying, if you want me to continue to pull this plow, or you could just get the sense of all the heavy work that these two individuals are doing, then you, Darboux, have to restore some harmony. So this is actually Will scolding Darboux. Do you love this? Are you reading the second paragraph? Because this newspaper is like a ship at sea. If the captain falls asleep or has fun in his cabin doing advanced mathematics, right, then the shipwreck will not take long. So Darboux has become very involved in his own research. He's let some things slide at the bulletin. Will's like, I'm going to quit doing this work unless you sort of get your act together. Which, by the way, he does. So this is actually a really highly successful collaboration. It ends in 1886 because that's actually when Will passes away, right? So they co-edit together until Will's death. What's interesting to me is not that it survives because they had these differences of opinion about the bulletin. They had this huge divide, which you might call an abyss, between their ways of thinking about mathematics. And I haven't given you really any evidence of this in the excerpts that I've shared. But there are two particular areas of disagreement, both of which have been written about quite widely. One had to do with solutions of ODEs, the other with foundations of analysis. These partly come about because of articles that are being reviewed in the bulletin and their discussion about the mathematics. And they partly come around, especially the foundations of analysis disagreement comes about because Will has written a textbook for his students on differential calculus. He asked Darboux's opinion about the textbook, and Darboux gives his honest opinion, which is fairly critical. There's this long dialogue. This appears in the letters for years. They continue to write to each other, one trying to explain to the other what their thinking is about these questions. And this is the Barnett Quazat, who has written his doctorate dissertation on Darboux. I think he says this really nicely. It's a dialogue of the deaf, right? There's really this dialogue of the deaf that is carried on between these two highly successful collaborators from an editorial point of view. But in the end, it's as if Darboux and Will no longer speak the same science. And I'll share one excerpt from Will because it's kind of a little bittersweet, right, that he's kind of sad about this. The actual exchange of the mathematics is really super interesting. If you get a chance to read it, you should read that. But here's Will saying, "This really saddens me. You want to explain the very first words of infinitesimal calculus, and I don't understand the slightest word of what you put so much goodwill into explaining to me." Right, so there's this recognition that it's still out of respect that they're talking to each other, but in the end, Will says, if you're right, then all I can think is about myself. I'm really nothing but an unintelligent mechanic, like I could do the mechanics. And there really is a transition in what's happening in analysis at this time that Despeaux is, and the German school is, on the leading edge, but Will clearly is not understanding what that new discourse is about. So, it's about going just about right on timing. Completely different situation with the Dedic and Vber collaboration. Again, I'll spend less time on this, but it's a quite different situation. So Riemann dies quite early, age of 39. He only publishes 11 works during his lifetime. And when Riemann dies, Dedican inherits his mathematical papers. He does more than that. So this is a letter that Dedican is writing to Weber, and because Dedican is actually charged with trying to figure out what's suitable still for publication among all these mathematical works that Riemann has left behind. And Dedican, again, this is the first letter he writes to Weber that starts their editorial collaboration. Dedican says, I found three things. Like, I found three things in all these papers from Riemann. The first is the one on trigonometric series, right, that was translated by Will for the Bulletin, a couple others. Those are the only ones in such finished form that I can print them soon. Everything else is in a chaotic state. And it took me a great deal of time to put together a few other fragments that are worthy of publication. So those few other fragments become 4 additional publications. These are actually done in collaboration between Dedican and Klepsch. This is Dedican's first collaborator on the collected works of Riemann's. And then Klepsch also passes away unexpectedly, and that ends that particular collaboration. It would be interesting to know what would have happened with the Riemann's collected works if Klepsch had not died, because he felt like they were done. He thought that these 4 last publications that we could find that are easy to find in the Riemann's papers, that's enough, we should stop. Dedican wasn't happy with that. Dedican really wanted to do more. He thought there was more in Riemann's papers that could be found and shared with the mathematical community. And this is when he turns to Weber. And Weber is, again, like a super good choice for a collaborator on this particular editorial project. So he's got this very diverse mathematical background. He apparently liked to move around. So he studied at several universities, PDEs, algebra, physics, topology. He had a pretty broad background. He taught at like 7 different institutions. I think he had something like 11 kids, so I don't know how he managed to move around so much in his lifetime. It apparently wasn't because he was a poor professor. I think he just liked moving. He happened to be teaching at Zurich when this collaboration started. Dedican was no longer in Zurich at that time. He was already back in Brunswick, but he happened to be visiting, so they actually met in person. And by then, Dedican and others already knew Weber for his works in algebra. So Weber's textbook was the leading German textbook up until the time of van der Waerden's modern algebra, right? So this was a highly influential reprinted publication. But kind of importantly in his research work, Weber also was at the cutting edge, right? So if you read the textbook and you read his research, they look like these 2 different discourses, these 2 different approaches to the subject, unlike what you would see in Will's work, where he was stuck in that one paradigm. Oh, in particular, Weber was familiar with Dedican's work, right? So that was an important part of this story as well. And then Weber was known as an expert on Riemann's function theory, right? So he was actually known as sort of an early defender of what Riemann did and an early explicator of what Riemann's work had been. So it was a really good choice for this particular project. Dedican was, of course, a super choice for this project in some sense, because he knew Riemann well. There's a reason why he was chosen. He was given charge of these papers when Riemann died. They studied together as students. They finished both their dissertations at more or less the same time. They taught for a couple years together at Göttingen afterwards, before Dedican went to Zurich and then Brunswick, and obviously before Riemann died. While they were at Göttingen, Dedican followed Riemann's courses. He attended his lectures. If you read Dedican's Nachlass, he has pages of notes where he's trying to figure out what Riemann was doing, and he tells Weber that. I am not a profound expert on Riemann's works, right? I know them, I believe in them, I do not master them, and I'm never going to. So Dedic says, I'm never going to master Riemann's works until I can somehow overcome my understanding of them with the rigor that is customary in number theory. He wants a different approach. So these two individuals enter into this editorial collaboration on the collected works. They take the rest of what's in these papers in Riemann's collected papers. This becomes very much an integral part of their two practices, Vber and Dedic, and it plays out in the series of letters they write to each other, where they try to decipher the text, they work out the details, right? They often have to reconstruct Riemann's reasoning because it's pretty obscure, right? And the end product is the first edition of Riemann's collected works. It has those. This really doesn't work very well. It has the papers that we talked about earlier that were published either by Riemann or just after his death. And then there's another 12 unpublished papers that Dedic and Vber are able to pull out of Riemann's papers. So one thing that I learned in preparing this talk that I probably should have known about before this, is this. Okay, there we go. Yes, I had known that the Dedic and Vber correspondence was published in German in 2014. But then there is a collaboration, since this is a talk on collaboration, it's a perfect thing to mention, between some historians in France and in Germany who were studying this correspondence and studying how this edition of Riemann's collected works was crafted, right? Both the influence of Riemann and Dedic and Vber, and then vice versa, how Dedic and Vber shaped not only our understanding of Riemann's works, but probably also the reputation, or what's the word I want for it, how they're viewed today. I think this is really fascinating work. And the name I will mention here is Emmylou Hefter, who is also part of the collaboration on Veblen. Yeah. So, really different collaboration than the one that took place around the Bulletin in France. In particular, Dedic and Vber go on beyond the editorial collaboration. They do this fairly deep mathematical collaboration that builds on all the work they did deciphering, understanding, crafting Riemann's collected works. This paper, 1882, which they write together, completely rewrites Riemann's works, but from a different point of view. See, this is actually an excerpt from the introduction to the paper, a standpoint which would be simple and at the same time rigorous and completely general. That standpoint is Dedic's framework of modules, fills, and ideals, which he had already used in his number theoretic work elsewhere. Right? And again, Vber is somebody who can understand that framework, and they completely rework Riemann's function theory from this point of view. Dedic now has all that rigor that he was hoping to have, which is customary in number theory. Here's a last excerpt from a letter from Dedic to Vber. This is about this particular collaboration around this paper, which, by the way, becomes the seminal paper in modern algebraic geometry. Right? It's considered like the seminal paper that sort of changes the way that field is approached. Dedic says, it would really bring me joy if this collaboration they're having would have some success, but he's not really counting on it. Right, so he's not really counting on this paper that they're working on to have get much attention, because people don't want to put up with tedious modules, and that's kind of correct. Although it's an important paper in the field, even Vber a few years later writes another take on Riemann's theory, and he does abandon the use of the modules and ideals for that. So, okay, here's that last. I'm good. Last promise, try to sort of say something that brings it all together, but there's nothing deeper important or, sorry, I tried. I think there's common ingredients here that you would just expect in a successful collaboration, right? Both of these collaborations, high level of mutual respect, clear dedication by both individuals to the endeavor, complementary contributions, not identical, but really equal commitments, and also clear shared vision of the venture at hand, right? In the bulletin, it's clear Will and Despeaux are committed to the same vision for what that should accomplish. And what's interesting to me again is they didn't need to have this shared view of mathematics. They were still literally not speaking the same science. But on the other hand, they couldn't go to the same extent where you see the Dedic and Vber collaboration end up, right? So that shared vision matters depending on the nature of the venture. And I think then I have references, and that's it. Thank you. Oh, pretty close.
Any questions for Janet?
Thank you. Okay. Oh, it's always standing as hard questions.
Why is it that Dedic has the responsibility for the Riemann?
Yeah, they were really close friends, right? They became quite close friends as students. They became they were teaching together. So it was Riemann's widow who asked Dedic take charge of these people. I actually don't know if it was something that Riemann had expressed a desire for himself, but certainly his widow wanted him to have. Yeah.
So did Dedic have anything to do with that famous paper that Riemann wrote on the zeta function?
The question is whether Dedic had anything to do with the famous paper that Riemann wrote on the zeta function. I do not know the answer to that. I'm sorry.
No.
Oh, but Fernando does. So yes. I mean, sorry. So the answer is no. Yeah. Yeah, nothing to do with it. That was published during Riemann's lifetime. Yeah, okay.
And,
Yeah.
and also, it's just orthogonal to anything that it can really be interested
Uh-huh. Yeah.
Last question from Kathy.
It's kind of tongue in cheek, but all the collaborations that I know that you do, when did you do all of this?
That,
All of these letters, like, did you capture them, or were they printed somewhere? And how
all the letters. Oh, so no, I mean, I get the letters from the secondary literature, right? So Hélène Gisbert made a lot of the Despeaux letters available and studied these, especially this, it's not a dispute, whatever, the confusion around foundations of analysis in the 80s. There were a couple of French doctoral dissertations on Will's and Despeaux's work in the 2010s, and then this German work is much more recent. Yeah. Okay, thank you so much.
So I want to start and echo what Janet and Victor said. I loved Sloan's talk yesterday. I hope you all were there, and it was such a great start to my day and MathFest. And this talk is going to come up very close to Sloan's work because I was at the same conference. But this is an audience participation talk, and so what I want you to do is take a minute to identify some topic or focus you've thought about recently, maybe recently as in the last month or the last year, and just jot it down. I'm going to give you like 20 seconds to do that, because I don't want you to forget it. In this modern world, you can type it in the notes of your phone. Okay, so once you have that, now I want to talk a little bit about the genesis of this talk. In November of 22, I was giving, or long before November of 22, I was preparing for an MAA distinguished lecture. And for the topic of that lecture, I wanted to talk about the monthly. And then in December of 22, I was going to this conference in Oberwolfach, and the group that I was assigned to, do you see that little yellow circle around Juan? We were at the same team. Yes, he is about half my age. And on the first day, he said about 2 words, which was Monday. But by Friday, we were having long, coherent conversations. He was my partner. And our project is, this is, when I get to the Institute for Advanced Study part of this talk, it's not the project I worked on with Juan, but it would be the project before the project I worked on with Juan. But what I want to do is look at the very, very beginnings of the American Mathematical Monthly and the Institute for Advanced Study, and these seem like institutions with very different aims, but actually what I want to really impart to you is that they have a lot of similarities in how they were begun, and those similarities can provide a template for how to start and sustain a mathematical initiative today. So I want to talk about the monthly first. This is the flagship journal of the Mathematical Association of America, and it was begun and has continued since 1894. If you're going to talk about the beginning of the monthly, the place to start is with Benjamin Finkle. And the place to start is with his name, Benjamin Franklin Finkle. I don't know anything about his parents other than the fact that they admired someone in our history, and they tasked their son with a living up to a very big name. So he was born in 1865, just 2 months after the American Civil War came to a close. He was educated in the rural schools of Ohio, and this would end up really playing out for the rest of his life, including on the pages of the monthly. He described himself not as a mathematical genius. He's described the classrooms that he attended as a young boy as very boisterous, not conducive for learning. But his half-brother brought him home a problem from the village store where the men used to gather to talk about politics and religion, and his half-brother brought him home a problem to think about because he thought he would enjoy that. And he had one influential teacher in these country schools. He attended the Ohio Normal University, which would later become Ohio Northern University, and then he taught in the rural schools of Ohio, Missouri, and Tennessee, so in the middle part of the country. And you can see he not only teaches, he actually moves into some leadership position. But relevant to this particular moment we're talking about, what's most important is that a colleague introduces him to the school visitor's mathematics department. And this is what we would call the School Visitor as a magazine, and the mathematics department is what we would call today a problems and solutions section. And so Finkle, very early in his life, starts working problems and solutions and submitting them to journals. He also starts a mathematics department at the University Herald at Ohio Normal University and sustains it past the time that he earns his master's. And in 1887, he decides he's going to compile all of these into a book. This is Benjamin Finkle's A Mathematical Solution Book with the rest of that title. It's 550 pages long. It takes him 6 years to get this published. I won't go into the details of it now, but I will say that this is very important training ground for him because he learns about the issues with publishing, in this case a book, but this would later become important for him when he launched the monthly. But he published this book really as a service to teachers. So it grew out of his experiences in the country schools and his observation that a work presenting a systematic treatment of solutions and problems would be serviceable to both teachers and pupils. This is the very first definition in the book. This will just give you an idea of the really very primitive nature of what this book begins with. He defines mathematics and splits it into applied and pure. My favorite part of this is number 8 on applied, etc., and etc. Just to give you an idea of what he's writing about at the beginning, it does get more sophisticated. He's talking about how to count objects by labeling the objects, not primarily to tell how many they are, and he identifies how to keep a tally of objects. And he gives some examples about how farmers keep track of their cows when they don't know how to count, and so on. But knowing that the status of the mathematical teaching in our high schools and academics was very deplorable, and even worse in the rural schools, I had the ambition to publish a journal devoted solely to mathematics and suitable to the needs of teachers of mathematics in these schools. And I decided to call the publication the American Mathematical Monthly. So this journal grew out of his observations in the country schools. And he began looking around for what Sloan would call a collaborator. He called it an associate. Having known of Professor Kela from Monterey, Virginia, through his contributions to the School Visitor, I laid my plans before him by correspondence and invited him to join me in the enterprise. So he found himself a collaborator from the problems and solutions sections. In the first volume of the monthly in 1894, so even though I have this older picture of Finkle, he's 29 years old when he launches the monthly. He outlines that the journal will devote its space to problems, papers, notes, and book reviews. That's the first volume on the left, and on the right is the current volume. And you can see we have all of the features that he started with. But it was really, for him, about problems. While realizing that the solution of problems is one of the lowest forms of mathematical research, and that in general it has no scientific value, yet its educational value cannot be overestimated. It is the ladder by which the mind ascends into the higher fields of original research and investigation. Many dormant minds have been aroused into activity through the mastery of a single problem. And the table of contents reflected his views. It's a 30-page issue. There were 19 pages devoted to articles. You can see Leonard Dixon published in the first issue in 1894. He was still a student then, but he would go on to anchor American mathematics in algebra and number theory. And there were 10 pages of problems. So a third of the first issue and subsequent issues were devoted to problems. This is the first problem in the monthly. Just to give you an idea, reduce 1/3 to eighths, and Finkle offered 2 solutions of the problems. I can tell you they have grown much more sophisticated since that time. As for producing the monthly, no help of any kind was employed and no expenses incurred, except those of printing, binding, and mailing the monthly. Mrs. Finkle helped me read practically all of the proofs and often addressed all the wrappers herself. For the 3 summer numbers of Volume 2, she read the proofs alone. So he also collaborated with Hannah Finkle. Mailing the monthly and producing it was a fiscal challenge. Finkle financed the first 19 volumes. He had some contributions, G.B. Halstead at Texas. When Dixon joined the board in 1903, he brought a subsidy from Chicago. When Dixon rolled off the board and recommended Slot brought a subsidy from Illinois. But printing costs escalated, and this became a serious financial issue. Slot took it on himself to raise the funding for the journal, first by bringing together some institutions to support the monthly, and second by going to the AMS. This is a very famous story, and he approaches the AMS in 1914, asks them to support the monthly. It's a committee of 5. It's a vote of 3 to 2 against supporting the monthly. Slot then wrote hundreds of letters to professors, and the MAA was formed in December of 1915. So the journal gave rise to the association, which is very rare. It's almost always the other way around. And I love this quote from Finkle: "I gave the monthly life, but Professor Slot, I hope, has given it immortality." And whether or not it actually is immortal, I can tell you this is the editorial board today, volume 130, and I hope we are still going strong. So, to begin the monthly, the idea reflected Finkle's longtime interest. It was a very human endeavor with a lot of work. I put that slash through Google. This was not a fast, let's look this up and get on with it. This was a long-time project for Finkle that just took on a new shape. Collaboration played a new role. It started with an ongoing idea, and funding was required. He had invisible and visible collaborations, meaning Hannah Finkle and also Kela, Halstead, Dixon, and some unexpected good fortune of Dixon publishing in the first issue and joining the board, which ultimately gave the journal a great deal of credibility. I want to shift to the Institute for Advanced Study, totally different organization, founded 36 years later in 1930. I think we're going to be hearing more and more about the Institute for Advanced Study since they have their centennial coming up in 7 years. But if you're going to talk about the Institute for Advanced Study, you begin on the corner in Newark, New Jersey with Bamberger's department store, which was started by Louis Bamberger, his sister Carolyn Fuld, who was married to Felix Fuld, and another business partner. In 1893, they bought a bankrupt dry goods store, and they grew it with 3 novel ideas of price tags, sales commission, and money-back guarantees. They grew it into a very large department store comparable to Macy's, Filene's, or Neiman Marcus. In January of 1929, a very important time period, Felix Fuld died. Louis Bamberger was 74, Carey was 65, and Louis and Carey decided that they wanted to sell Bambergers and devote the rest of their lives to spending their veritable fortune. They really wanted to, they were Jewish, they wanted to endow a medical institution, a medical school for Jewish students, and so they had their advisors. I think that's what you have when you have this kind of money. I actually don't know personally. But they had their advisors, Leidesdorff and Moss, go out and try to find out how to start a medical school in New Jersey for Jewish students. And in their investigations, that took them to Abraham Flexner. I do have something in common with Abraham Flexner. He was born in Louisville, Kentucky. His older brother Simon, you may have known of him for his work on the Rockefeller Foundation. His older brother paid for him to go to Johns Hopkins University. He loved Daniel Coit Gilman's, that was the president of Johns Hopkins. He loved his vision for the institution, which was focused on research and teaching. In the end, Gilman had to allow undergraduates to attend Johns Hopkins. This was really a frustration for Flexner. He would have loved for it to be a research institution. He returned to Kentucky. He taught at Louisville Male High School, where my mother would attend a half-century later. And then he started a bunch of innovative, basically non-traditional schools. His wife was a teacher and a very successful playwright and writer. And she wrote a very successful play, and with the money from that, he was able to go to Harvard and study psychology, which then took him to Germany. He never finished his degree, but he wrote a very important book called The American College of Criticism, where he criticized American institutions, said they were not as strong as their German counterparts. This came to the attention of Henry Pritchett, who was the director of the Carnegie Foundation for Advancing Teaching, and he asked Flexner to write a study of medical schools in America. Now you were wondering, how were we going to get back to the Institute? Well, he published his study in 1910. This is a very important study. It's one of the most widely cited works in any study of education. It's called the Flexner Report. It became the template for how to run a medical school, which is still in use today. So Flexner argued for a 4-year medical school, 2 years of intensive scientific study, and 2 years of clinical training. And he included a map. This is the New York Times story on the map, where he identified the schools that were really strong and the schools that were weak, and he argued that all the weak schools close and all the money be funneled to what he considered the strong schools. And that is exactly what happened. 89 of the 155 medical schools closed in the next 15 years. That led him to attract the attention of the General Education Board at the Rockefeller Foundation, where he became a secretary, and that ultimately he was invited to give the Rhodes Lectures at Oxford in 1928. He gave these lectures and ultimately compiled them in a book called Universities American English and German, where, without knowing, he would outline the template for the Institute for Advanced Study. In particular, he argued that progress would be assisted by the outright creation of a school or institute of higher learning, a university in the postgraduate sense of the word. It should be a free society of scholars, free because mature persons, animated by intellectual purposes, must be left to pursue their own ends in their own way. It should furnish simple surroundings, books, laboratories, and above all, tranquility, absence of distraction. And then in his autobiography, he wrote, "How much effect did the Rhodes Lectures have had? I have no way of knowing. One important result they promptly had. I was working quietly one day when the telephone rang, and I was asked to see 2 gentlemen who wished to discuss with me the possible uses to which a considerable sum of money might be placed." And instead of arguing for a medical school, which was what Leidesdorff and Moss had come to ask him about, he said the time was ripe for the creation in America of an institute in the field of general scholarship and science, not a graduate school training men in the known and to some extent methods in research, but an institute where everyone, faculty and members, took for granted what was known and published, and in their individual ways endeavored to advance the frontiers of knowledge. He met with Carolyn Fuld and Louis Bamberger, and by June of 1920, Bamberger and Fuld had given $5 million, which is $181 million in today's dollars, to establish an institute of advanced learning. That fall, he left on a journey through America and Europe to look for faculty and to gain ideas for what the template for this institute should be. This photo is from 1921. I just really love it. However, when he was abroad, he met with Einstein to encourage him to join the faculty. And equally as important, he met with Veblen. He bumped into Veblen actually at Göttingen. And this turns out to be a really fortunate event. And he asked Veblen if he would be interested in this institute. You met Veblen in Sloan's talk, just in case you weren't there. He had earned his PhD from the University of Chicago in geometry in 1903. Woodrow Wilson, who was president of Princeton at the time, invited him to be a preceptor at Princeton. He began his long career there, where he ultimately became the fine professor. He was AMS president in 1923 and 24. He's very celebrated in 1924 because he was able to garner NRC fellowships for mathematicians by arguing how mathematics is related to other sciences. But in the same letter where he asked Vernon Kellogg, who was secretary of the NRC, for these fellowships, he also proposed a mathematics institute. This was in 1924. So the two ways to advance mathematics in America, Veblen felt like, were these fellowships and a mathematical institute. The physical equipment of such an institute would be very simple: a library, a few offices, and lecture rooms. Sounds a lot like Flexner, doesn't it? And a small amount of apparatus such as computing machines, but the main fund should be used for the salaries of men or women whose business is mathematical research. There are plenty of men in the country who've showed that they are capable of living up to such a position. So this was the Veblen that Flexner was proposing, hey, would you be interested in my institute? The work that Juan and I did is about their relationship, planning the institute and faculty, and there was a tension because Flexner was very interested in a very strong faculty. Veblen was very interested, he was interested in a strong faculty, but he was also interested in building a physical structure and acquiring land. And as Flexner described him, he was a most excellent person, but the word building or farm has an intoxicating effect on him. So the Institute for Advanced Study has had at least 34 Nobel laureates. It accounts for more than 2/3 of all Fields medals, more than 9 Nobel Prize winners. It's called the University to Universities because when you go there to do your research, you go back to your university and you're really revived and rejuvenated. But Flexner and Veblen also had some behind-the-scenes help, Mrs. Esther Bailey. So we meet Esther on the pages of Universities, Flexner's book, where he says, I'm also once more bound to express my appreciation to my secretary, Mrs. Esther Bailey, who has assisted me in the collection of illustrative data, has checked statements of fact, and practically put the volume through the press. She also managed the budget at the Institute. So letters from Flexner to Veblen are always like Flexner saying, well, Mrs. Bailey has told me we have this much, and Mrs. Bailey has told me we have this much. She attended board meetings, she was his right-hand woman, and she maintained personal relationships with the Institute colleagues. Carolyn Fuld was also a behind-the-scenes collaborator. Bamberger was really involved in her brother, the negotiations, the financials, but Carolyn Fuld really took care of the faculty members. She was especially enamored with Einstein. And of course, it was A.M. Flexner's money that allowed Flexner to go to Harvard and travel to Europe to study. So the beginning of the Institute for Advanced Study also reflected Flexner's and Veblen's longtime interests. Collaboration played a key role. In this case, they had funding to give rise to an idea instead of having to fund it personally themselves. There were invisible and visible colleagues. I left Luther Fehler Eisenhardt here. He's another person involved in this collaboration. And the unexpected good fortune that when Flexner bumped into Veblen, Veblen had already thought about this. I do want to point out that Flexner was 64 when he started this work with Bamberger and Fuld, so there is a definite contrast in age here. So if you want to think about the beginnings of these two institutions, what can we learn from them? First, the structure of the idea had been in place for a long time. These initiatives were not conceived in haste. 1.5, this is really my work with Juan. It takes time for ideas to gain momentum, and there's some tension involved. I think for Finkle, the tension was definitely related to financially sustaining the journal. And for Veblen and Flexner, it was this tension in their two different priorities. This may not be unique to mathematics. I got to do at Sloan. Last Sunday, hot off the press, literally 5 days ago, the New York Times interviewed Christopher Nolan, director and writer of the new Oppenheimer film. And the interviewer said, "It's hard to believe you ginned this up in such a short time since Tenet." And Nolan says, "I wrote the script relatively quickly once I started writing, but I had worked a lot out beforehand. Many years ago, I'd written a script about the life of Howard Hughes that never got made because I wrote it right as Scorsese was making his film. But that gave me a lot of insight on how to distill a person's life and how to view a person's life in a thematic way, so that the film is more than the sum of its parts. So in some ways, the script, yes, it took me a few months, but it was really a culmination of 20 years of thinking." So I think if we extended this further, we might find this is true of other types of initiatives. Finances matter, and the more secure, the better. There are visible and invisible colleagues. There are unexpected blessings and good fortune. As I mentioned, Dixon, published in the first issue of the monthly, joined the board and then went on to become a very strong force in American mathematics. E.H. Moore published in the monthly, G.B. Halstead. Veblen and Flexner had a chance meeting, and it just so happened they had both been thinking of an institute. Now yours. I ask you to write down something you've been thinking about. There's the kernel of your initiative. So get going and dream big.
You have to write a nice fancy sounding title when you're going to be talking about a bunch of crackpots. So, all right, so I also wanted to thank Sloan for the invitation to participate in this session and kind of repeating what other people have already said. Yesterday, she shared some intriguing projects undertaken by teams of historians, mathematics, and other scholars. This afternoon, we've heard about many examples of research, editorial, and organizational collaborations that span the ancient through modern periods. As the panelist who holds a history PhD and has taught the major schools of historical interpretation to multiple cohorts of undergraduates, I would like to spend a few minutes adding another dimension of collaboration to what has already been said about collaboration as a means for undertaking historical research and writing, and as a topic that we observe in the past. However, since I am also the panelist who is speaking late in the day and standing between you and getting to see Della again with the Hom Sigma lecture, I will spend most of my talk telling some hopefully entertaining stories about a few of the kooky characters I study who lived in the first 2/3 or so of the 19th century. These stories, though, I think, convey some of the richness and types of collaborations that emerge when we start looking for those relationships. So here's the historiographical part. About 8 years ago, I spent a decent amount of time thinking about how the concept of mathematical communities functions in two ways: as a topic that historians of mathematics might identify in defining the scope of a project, i.e., I am researching X group in Y location during Z time period, and secondly, as a lens through which we can draw conclusions about the historical significance of past events. So in this article, I argued that when we pay attention to the politics, power relationships, and discourse of the mathematical community of American professors of mathematics and natural philosophy in the first third of the 19th century, then the motivations of Jeremiah Day in preparing a series of mathematics textbooks are cast into sharper relief. He intended to influence philosophies of teaching mathematics along the entire Eastern Seaboard, not merely in his own classroom at Yale. And indeed, Day successfully used his platform to convince his community that the primary justification for teaching mathematics to every college student was the subject's ability to discipline the mind for other intellectual endeavors and for daily life, thus shaping the content and structure of American mathematics education for several decades. Similarly, kind of at the back of my mind, I'm mulling over how mathematical collaborations have the potential to serve as a theoretical approach to historical interpretation as well. If we use collaboration as a lens through which to view primary source evidence, what can we learn about the relative power wielded by the participants in these partnerships, both with each other and with other mathematicians or the general public? How did collaborations influence the actions undertaken by these insiders and outsiders? Did collaborators use language that was specific to the collaboration? To what effect? How might collaborations be used in concert with other methodologies, such as book history or critical biography, to uncover additional layers of the past? I have not yet developed these thoughts into a formal theory, although I think we've seen some of this in action in the first 3 talks and Sloan's talk yesterday. But here I'll just stop with raising these questions about what characteristics or facets of the past might be opened up if we think of the past as comprised of collaborations. And yeah. All right. I have more or less stayed on track, so we have about 15 minutes to explore some of the types of collaborations from my work on the History of Textbook series in 19th century American mathematics education. These are the typologies that popped into my head shortly after I received Sloan's invitation to join this panel. We have already heard quite a bit about correspondence networks in the previous talks, so here I will just mention one exchange of gossip and advice that served as what I will call a self-interested collaboration in the preparation, selection, and reception of textbooks. One significant step in the teaching of geometry in American colleges was the replacement of Robert Simpson's 1756 The Elements of Euclid, which was intended to be a restoration of the original text, with John Playfair's 1795 Elements of Geometry, which introduced some arithmetic symbols to help students understand proportion, and which in its 1804 second edition reworked and reorganized the material on solid geometry. Although we know little about him today, the man apparently behind this transition was Francis Nichols, a bookseller who is credited with publishing and authoring a few mathematics and geography textbooks. He seems to have been mainly based in Philadelphia, although he showed up in New York and Boston as well. His correspondent in this exchange was Jeremiah Day, who compiled a series of 4 textbooks between 1814 and 1817, and who survived a life-threatening illness to become Yale's professor of mathematics and natural philosophy in 1803, and Yale's president in 1817. Reading his correspondence and his works, he seems like he was a genuinely nice person, but what always stands out to me is that the chronically ill person who outlives everyone is a trope of 19th century novels, but in Day's case, it was real life. Despite his weak heart, he survived 2 wives, 3 of his 4 children, and numerous faculty to live to age 94. When we pick up his story on March 10, 1806, Nichols had already convinced Day to switch Yale from Simpson's textbook to Playfair's. Nichols was now writing to talk Day out of changing his mind because Nichols had run into production delays. By reason of the bad faith of an engraver, my edition of Playfair's Geometry is not ready. The 6th book will be finished this week, so there would have been 3 more books to print after that. I have employed another engraver and expect that the whole work will be printed in 5 weeks, but this will depend entirely on the industry of the engravers. The 2nd edition of Playfair's Euclid is far superior to Simpson's Euclid and may be read by a student in less time and with less labor. So what Nichols was saying is, please don't cancel your order, you need the sale. He went on to suggest that Day could keep the class busy with an activity like algebra for a few weeks while they waited for the textbooks to arrive, since the students would be able to master this clearer and simpler approach to plain and solid geometry so quickly. You can read some of the things I've written about Playfair's Geometry and see if you agree. We know from sources such as course catalogs that Day and Yale did adopt Playfair's Elements of Geometry. This series of letters adds that a year later, Nichols was tracking down a missing box of copies, which had not yet made it from Philadelphia to New York, let alone the rest of the way to New Haven. After Day stopped working on his own textbook series in 1817, he sought collaborations with John Farrar of Harvard, as well as with Nichols, to extend and update the mathematics curriculum at Yale. I will say a little bit about the complicated publication history of Farrar's series in a moment. In his letters to Day, Nichols shared news about the printing of Farrar's volumes, assessed the quality of their contents, and voiced strong opinions about how much mathematics was realistic in the American college mathematics curriculum. For instance, he wrote, "The first volume of Lacroix's algebra is being printed at Harvard, making above 160 large pages octavo, without the long introduction. Several algebraical subjects are still wanted or omitted. Nonetheless, Farrar's selections from Francis Horner's 1797 translation of Euler's Elements of Algebra, together with Lacroix's algebra, will amount to more than 500 pages, or twice as much algebra as is read at Cambridge in England." Day's responses do not survive, so we do not know whether Nichols' assertions provided the sort of collaboration in selecting textbooks that Day was seeking. Nichols attempted one more self-interested collaboration at the end of his last extant letter today, but it appears that the shortened version of Playfair's Elements that he described never found an audience at Yale or in secondary schools. So that's what that quotation is about. Because Harvard's president and governing boards involve themselves in its development, the Cambridge Course of Mathematics and Natural Philosophy, the textbook series spearheaded by John Farrar, is an example of what I am calling administrative collaborations. Indeed, the record suggests that after he was promoted to Hollis Professor in 1807, Farrar remained satisfied with the status quo of the curriculum, which relied heavily on Playfair's Elements and a 2-volume compendium, Mathematics Compiled from the Best Authors, that was published in 1801 by Farrar's predecessor, Samuel Weber. Farrar was only called away from his advocacy for purchasing astronomical instruments and constructing an observatory by a May 1816 directive from the Harvard Corporation to review and update Weber's mathematics. 8 months later, Farrar reported that he had found it impossible to incorporate an improved treatment of algebra into those chapters of mathematics. He continued, quote, "From what you said, I considered myself as authorized to substitute new treatises both of algebra and trigonometry." The administration's view of their collaboration did not, in fact, include unilateral decisions by Farrar. So Harvard records have this series of back and forth communications and go on for at least 2 years. Farrar even recommended at one point that Harvard use Day's series of textbooks, but as he wrote today in April 1817, quote, "Old institutions and large bodies are slow in making improvements." Indeed, in March 1818, Harvard set up another committee to study mathematics textbooks. 9 days later, Nichols wrote one of the letters we talked about a few minutes ago, in which he noted that the publication of Farrar's series of translated textbooks was a fait accompli, with 3 volumes available for sale or in press. However, the administration at Harvard would continue to chime in on, or interfere with, based on your point of view, Farrar's decisions about mathematics curriculum and textbooks until he retired in 1836, and this was in a severe illness, and I tend to take Farrar's side because he's just such a sad sack by the time he retires. But now I'm going to kind of counter that impression of Farrar. His series is also notable for what we might think of as unacknowledged collaborations. Biographical encyclopedias usually imply that Farrar translated all 13 volumes himself, but as we saw with Nichols' letters today, his contemporaries knew that he sometimes republished existing translations, such as Francis Horner's version of Euler's Elements of Algebra. Further, Farrar's colleagues were aware that at least some of the textbooks that had not yet been translated from their original French were prepared by Farrar's students and other assistants. For example, the letters from Nichols today also tell us that, quote, "A young man was translating Legendre's Elements of Geometry for Farrar in October 1818. Although the translator's actions were described in the advertisement, announcement, or preface in contrast to the actual advertisements we'll see in a couple of minutes, when the book was published in 1819, the name of the translator was not mentioned. In contrast, Farrar at least admitted that he, at a minimum, had had help with completing the translation of Bézout's First Principles of the Differential and Integral Calculus in 1824, although again, he did not identify his assistant. Because he said so in his own memoir, we know that this assistance was provided by educator and Harvard alumnus George Beryl Emerson. We do not, however, know whether the collaboration predated Farrar's departure for the Azores with his ailing wife, which is what prevented him from seeing first principles through to publication. Still, unlike translators such as Horner, Emerson at least knew that he was participating in a collaboration with Farrar, and he could expect at least some public acknowledgement of his role. When I referred to Nichols' printing of Playfair's Elements of Geometry earlier, I glossed over the fact that Playfair and his publishers in Edinburgh had no idea what Nichols was up to, so this American edition was totally pirated. Of course, the lack of international copyright laws at the time meant that Nichols and his printers experienced no consequences. More broadly, Americans appropriating and sometimes outright plagiarizing by omitting the original authors' names turned European mathematics professors into unwitting collaborators with their American counterparts. One of the most blatant plagiarizers was Charles Davies, who got his start in academia at the United States Military Academy at West Point, New York, and who published approximately 50 mathematics textbooks that range from arithmetics for small children to calculus for upper-level undergraduates. For example, over the course of several editions in the 1820s and 1830s, Davies co-opted an 1822 translation of Legendre's Elements of Geometry by Scottish historian Thomas Carlyle and made it known to Americans as Davies' Legendre. In each of these first several printings, Davies made changes to the text, such as inserting what he called references to particular diagrams, so maybe his plagiarism got less blatant over time. Still, I put the Ross up here because a professor who waits for a colleague to go on active duty and then slaps his own name on the colleague's translation, which is what Davies did in 1835 to Lieutenant Ross's 1831 rendering of Borden's Elements of Algebra, seems like a jerk. So Davies did actually get sued for plagiarism once in his lifetime by another American. Although ironically, the more I look at the case records and the two books, the judge at the time signaled that he was leaning toward the plaintiff, but it's starting to look like Davies may have been innocent. This suit took place in 1845. It was filed by Frederick Emerson, who had published North American Arithmetic Part First in 1830, and the complaint was about Davies' 1840 First Lessons of Arithmetic. Kind of regardless of what happened, the case ended up being settled as Davies' publisher, Alfred Smith Barnes, paid an out-of-court settlement. Davies and Barnes had a 40-year relationship that represents the final type of collaboration I will consider today, the promotional collaboration. They teamed up in 1838 when both men were living in Hartford, Connecticut. Davies provided the textbooks and their reputation for quality, since professors who were trained at West Point tended to choose his series for their institutions. Military theorist and West Point colleague Dennis Hart Mahan wrote in his 1837 textbook, An Elementary Course of Civil Engineering, quote, "Without wishing to prejudice the works of others, the author would call attention to the very complete course of mathematics of Professor Davies, late professor of mathematics in the Military Academy, as the best that has fallen under his observation in the English language." Barnes's contribution was to travel around New England, visiting colleges, academies, and common schools for 2 years, playing baseball and other games with the students, and converting instructors to the virtues of Davies' textbooks. As their market share and publishing house expanded, Davies also began to prepare intricate print advertisements. So these eventually divided up Davies' series by educational level and showed how schools could rely on Barnes's authors for every subject. Even though Davies never took an active interest in the business side of their enterprise, I would not be surprised if he contributed some of the claims made about the influence of his textbooks, given the governmental and military references in this list. Both men used 3 words in particular. They offered complete textbooks that set the standard for a national audience. Their marketing was successful. For instance, in 1853, Davies' name was on 200,000 of the 800,000 books sold by Barnes's firm. During his lifetime, 5 million copies of Davies' books were printed. And if you want to read more about this, one of my own research and writing collaborations was the 2008 monograph, Tools of American Mathematics Teaching, with Peggy Aldrich Kidwell and David Lindsay Roberts. The first chapter is about textbooks and mostly about the marketing of American textbooks by Davies and Barnes. So I tried to do two things as we wrapped up this session on collaborations in the history of mathematics and collaborations by historians of mathematics. First, I briefly made a case for thinking of mathematical collaborations not only as a terrific topic of study for historians of mathematics, but also as a methodology for thinking about why the past is significant. Second, I offered several possible categories of collaborations: self-interested collaborations, administrative collaborations, unacknowledged collaborations, unwitting collaborations, and promotional collaborations. While collaborations in which new mathematics were created matter a lot, it is important to look at these other kinds of collaborations too, as they influenced what mathematics was communicated and taught, as well as who got to participate in mathematics. Thanks again to Sloan for organizing this session, and thank you all for your attention at this late hour of the day.
Thank you, Amy. Do you have any questions?
Do Davies and Barnes share the sort of promotional vision, or is Barnes the actor?
Yeah. It's, as far as I know, there's no surviving correspondence, so a lot of what we know comes from, there are a couple histories of A.S. Barnes and Company, which turned out to be one of the largest book publishers, particularly textbook publishers, of the 19th century, and became American Book Company in the 1880s and 90s, but now has gone away. People always ask if it's Barnes & Noble, and it's not. So, yeah, so it's hard to know what their conversations comprised. Barnes was about 20 years younger than Davies. Davies was looking for ways to make money on textbooks. And so I think you've got the energy and the desire kind of working together.
All right, let's thank Amy.